Welcome to Coulomb's law. Coulomb's law recognises that force between two charges has this relationship, being the distance between those two charges. We can turn this proportional sign into an equals and make the equation of Coulomb's law. So in order to do this, we take these variables and we put a constant of proportionality in front of them. The constant of proportionality is usually called k, but k can consist of many algebraic variables. So we have our charges and the distance or the radius between them squared. Notice that this is an inverse square law. Here we have the radius squared on the bottom, so we could split this up and say that this is true, and this would be an inverse square law. Inverse being on the bottom of the fraction and the square. So over here we're going to put the constant of proportionality, which consists of 4 pi epsilon subscript 0. The 4 pi originally comes from this equation here. This is for the surface area of a sphere, and we know that any point source of anything, if we think of this as a light source maybe, we can measure the energy output as being on the surface of a sphere getting gradually further away. So the r squared and the 4 pi comes from this concept. The epsilon subscript is the permittivity of free space. And this is a measure of how easy it is for an electric field to penetrate a vacuum. It has the value sometimes written as this. The permittivity of free space and the permittivity of air are very, very similar. So if you're doing this experiment and the material between the charges is air, it's okay to use that value. If we have an object with a positive charge and another object with a negative charge, we can measure the force of attraction between them. Notice that Newton's third law tells us that these forces are equal and opposite. If we know the distance or the radius between them and the charges on each object. For example, this might be a proton and this may be an electron. If you are dealing with large spherical objects, for example, the nucleus of an atom, and you may only have a single electron over here, then what we do is we take that radius to be from the center of the sphere. We know that if you have two positive objects, they are going to repel. Or two negative objects, they are also going to repel. Coulomb's law will allow you to calculate the magnitude of this force. Make sure to put the signs of the charges in here, so that if you have a positive and a negative, your answer will come out as negative, so you know that it is an attractive force. For example, this situation over here. If it is two like charges, you will end up with a positive force, like this. You may occasionally come across the relative permittivity of a material. This value is a ratio of how many times it is the permittivity of free space. So for example, air has a relative permittivity of 1.0006. It is almost exactly equal to the permittivity of free space. The way we calculate the relative permittivity is by taking the permittivity of the material and dividing it by the permittivity of free space. So because this value is almost exactly the same as this value, you end up with a value close to 1. For comparisons, the relative permittivity of water is equal to 80. So it is 80 times the permittivity of free space. Compare that to the relative permittivity of air. And you can see that air resists an electric field going through it much less than water does. If we compare Coulomb's law to Newton's law of gravitation, we can make several interesting comparisons. So for Newton's law of gravitation, we have the same format of equation, but instead of charges, we know that gravitational forces exert on masses. So instead of charges, we have mass, but other than that, the equation is the same. When we turn this into the equation, we still have the same format, only the constant of proportionality is big G. For Coulomb's law, that constant of proportionality has a value of 9 times 10 to the 9. For gravity, this value is 6.67 times 10 to the minus 11. This means that the force of gravity is approximately 1 times 10 to the 20 times weaker than electrostatics. It is not known why gravity is so weak compared to electrostatics. It is an area of current research. One of the many theories is that gravity is actually spread and shared across multiple dimensions, and that's what makes it so much weaker. Here is an image of Charles-Augustin de Coulomb. He was a French physicist operating mainly in the 18th century. He discovered this relationship between charges by inventing a new piece of equipment called a torsion balance. Torsion is a word that means twisting. In this image, we can see that he is holding the piece of equipment that he invented. And here is a schematic of that torsion balance. It works by hanging a bar with a charged object on one end and countermass on the other by a long, thin piece of wire. This system is allowed to reach equilibrium where all the forces are balanced. If you bring an object with an opposite charge close, then you will get an attractive force pulling and moving this orb towards the left. By rotating the wire in the other direction, you can create a twisting force that brings the orb back to its original starting position. And the twist that you are applying to the wire can be measured. And it was found that this twist that needed to be applied to bring everything back into balance again was proportional to the size of this charge. This twist here was providing a restoring force, a force to bring things back to equilibrium. He invented this torsion balance in 1784 and published Coulomb's law the following year. In 1889, Gustav Eiffel completed the Eiffel Tower, and at 330 meters tall, it was the largest structure on the Earth. This is almost double the height of the previous tallest structure, which was the Washington Monument. And it remained the tallest structure on the Earth for 41 years. If we have a look at some of the inscriptions on this tower, we can see the name Coulomb. There are other names here as well, some of which you may recognise, some of which you may not. In total, there are 72 names inscribed around the outside of the Eiffel Tower, celebrating French engineers and scientists. Here are some of the names that you may recognise from A-level physics, chemistry, biology, and mathematics. Lagrange, Fizeau, Arago, Poisson, Carnot, Ampère, Gay-Lussac, Becquerel, Malus, Fourier, Lavoisier, Navier, Le Chatelier, Coriolis, Fresnel, and Foucault. And here we can see Coulomb.